Hey guys, we're going to be looking at lesson 6.1 and 6.2 today. So that's the characteristics of an exponential function. So we're going to figure out what an exponential really is. We're going to go to our definitions, fill them out. So just make sure that you're on lesson 6.1 and 6.2 in your yellow booklets that you guys got today. Okay, so example number 1, they're saying which of these are exponential. So let's see what each of them are. So if you guys look at part A is something that you did in grade 10. So in grade 10, you guys started to study and you studied linear equations. So where it's kind of like a sloped line, like a line that's gradually either decreasing or increasing. It can be really quickly increasing or quickly decreasing. So it's kind of like a slanted line. So this is a linear equation or a linear function in this case. And then we have last year, you guys looked at in 20-2, or if you were in 20-1, you looked at quadratics. That's what these two guys are. These are quadratics. Quadratic functions, where they're in that parabola shape. So this can be representing a ball being thrown up into the air and falling. So these are both quadratics. Last year in 20-2, you studied that this one is an upward facing parabola. So this guy right here is an upward facing parabola. This one here was a downward facing parabola. So this was 20-2 or 20-1. This was 20-2/20-1. Okay, and then this was 10C up here. Okay, so what we want to do is figure out which of these left over are exponential. So exponential can be used to represent population. So population can grow very, very quickly if you have a lot of resources available. Okay, so we're talking about like population of rabbits. They multiply really quickly. So these two guys are exponentials. Okay, so the reason is that this one is increasing very quickly, or you can actually decrease very quickly as well. So let's say on Earth, if we have a lot of resources, it would look like this. If there's enough food for everyone to eat, then the population is going to quickly increase. Versus if we took away everybody's food, if all the food on planet Earth went away, no resources were left, what do you think would happen to that population in the world? So in that case, it would quickly decrease. Everybody would pretty much die off. Because there would be no resources, nothing to feed everyone. Okay, so that would be, these are exponentials. So this one is an increasing exponential versus this one is a decreasing exponential. Okay, so what I'll get you guys to do is go to your definitions page. So flip back. So today we're doing lesson 6.1, 6.2, and 7.1. They're all the same thing, and they're nothing new, so that's why we're doing them all together. Okay, so let's go to our definitions page, and we're going to look at exponential functions. So exponential functions can be either increasing, where they increase very quickly, or you can have exponentials that decrease very quickly, so they look like this. Yeah. Okay, so an exponential function, if you were to write it, it can look like this. Y equals a times a base to the power of x. What you're going to notice is that the variable, in this case, this is new to you guys, the variable is your power. The variable is a power. It's in your exponent spot. Okay, so instead of you having like 2 to the power 4, like we did in 10C or in other times, now we have x as our power. Okay, so what we'll do is we'll always fill in a with a value, and b with a value. B can never be equal to 0 or 1. So they're not allowed to equal 0 or 1. Those are called bases, okay? Bases, and this guy right here is called your coefficient of A. Coefficients and bases, this right here, base, cannot go together. They cannot ever multiply together. Remember that, guys. That's a common mistake that I find. So do not multiply ever your coefficient and your base. They're separate items. And we'll see what that coefficient does. So this is an example of an exponential. Y equals, you can have 2, and the base could be 4 to the power of x. Okay, so that would be an example of an exponential. So what we're going to practice is graphing it now and then seeing what it looks like. Before we flip back, we're going to look at also Euler's number in our definitions page. So Euler's number is the letter E. E is just like pi. It's this number that goes on forever. So E, if you actually, I'll show you where that is in your calculator, but it actually represents a value like, for example, I think it's like 2.717 ... goes on forever. Goes on forever. So just like pi, pi is used so commonly when we talk about math that we use that symbol to replace it. E is so commonly used in financial situations that they use the letter E instead of 2.717 as a ratio. So they made their lives easier by having more decimals in that E value. So letter E just represents Euler's number. So I'll show you where to find that later on. Okay, so these are the first 3 definitions, and we might come back to this later on, but right now we'll go back to lesson 6.1 and 6.2. Okay, so what we're going to do is we're going to practice graphing each of these guys right here. Okay, so you're going to want to use your graphing calculator, and I'll show you how to put these values into your calculator. Okay, so the first one that we're graphing is 8 in brackets, then 3 over 4 to the power of x. So 8 multiplied by your base of 3 over 4 to the power of x. So you're going to start by pressing y equals. So you're going to use your button on your calculator, and you're going to go to y equals on your graphing calculator. Okay. Once you have, your screen looks like this, you're going to put 8 first. In brackets, you're going to write 3 divided by 4, or you can use your fraction button if you're familiar with that. So 8 in brackets, 3 divided by 4. And then you're going to use this little house roof here. Do you guys see that little arrow that points up where it looks like kind of like a house roof? That's your power button right here. So you're going to say power of x. Okay. So once you have that in your y1, I want you guys to go to the window. So press window. So take a second and put that into your calculator. 8 in brackets 3 over 4 to the power of x. Okay, so once you have that, press your window. So this is your standard window that we're going to be using for most of these equations. So it will change eventually, but right now we're going to stick on this. So we're going to have our x minimum being -10, our x maximum being +10, our scale being 1, our y minimum as -10, and your y max at 10, and your y scale at 1. Don't ever change that resolution or anything after that, okay? So the first 6 numbers are the only ones we ever have to adjust or play with. The rest don't touch, okay? So -10, +10, 1, -10, +10, 1. Okay, so make sure that your values show this. Once your window is set to this, I want you guys to press this button that says graph. Okay, so if you see this little kind of this yellow piece right there, it just means that you're thinking. So it might take a little bit for your graphing calculator to do this. It's just a thought process. Okay, so if you look at this, you want to ask yourself, is this an increasing or decreasing exponential function? So this one is going down, and in this case is going down to the right. Okay, so if it starts off high and then goes lower and lower and lower, that means it's a decreasing exponential function. Okay, the questions that they want us to ask for this one are, what are the x-intercept, the y-intercept, the end behavior, domain, range, and if it's increasing or decreasing. Okay, so let's start by finding the x-intercept. So if you look at it, do you guys think that it's going to touch your x-axis? So the answer should be no, it does not touch your x-axis. In this whole unit, whenever we have exponentials, they will not touch your x-axis. Okay, so you're never allowed to have your y value being equal to 0. There's no power that you could put a number to that would ever give you 0. So that's why it does not exist. So for each of these questions, whenever it asks you for the x-intercept of an exponential, you're going to say that there is none. Okay, so step 1, what I want you guys to do is create a sketch of what you guys see on your graphing calculator. Okay, so we have something that looks like this. And what you want to do is show arrows on both sides. You want to show that this graph continues on both sides. This is your x-axis, this is your y-axis, and then we want to label. So we want to start by saying that there are no x-intercepts. Then our y-intercept. To find that in your calculator, you're going to press second, trace, 0, enter. So those are the buttons that you can do in your calculator to find that. Okay, so in my calculator, I'm going to press, actually I can shorten my steps, so I'll show you a faster way. So instead of pressing second trace, just press trace. So that'll actually be a little bit easier. So trace, 0, enter. So let's do it that way. So we're going to press trace first. When you're on your graph, you're going to press 0 and then enter. The y coordinate is your answer. So if you look at it, this is my answer right here, where y is equal to 8. Okay, so when I press this, I found that y equals 8. Now, if you look at the original equation that we entered into our graphing calculator, this right here, you should notice that there's a similarity between your y-intercept and the equation that you see. This guy right here in front of your base, this guy is always your base. Your base is always attached to x. The number in front of it should be called your coefficient. If there is a coefficient, your y-intercept is what is in that place. So in this case, our y-intercept is 8. So we want to label this as the y-intercept as well. Your coefficient is your y-intercept. Okay, so we have our y-intercept, we have our x-intercept. Now we're going to talk about end behavior. So what we want to do is we want to label our quadrants. So last year in trigonometry, you should have learned that you're labeling quadrants. So this is for 20-1. They labeled quadrants as this is quadrant number 1, this is quadrant number 2, this is quadrant number 3, quadrant number 4. Okay, in 20-2, you probably didn't really focus on that. So that's why I'm showing you how to do that. So it's quadrant 1, 2, 3, 4. So what we want to do is we always want to look at the graph from left to right and say what quadrant do we start in and what quadrant do we end in. If you guys look, the end starts in quadrant number 2 because you're on the left side. The right end ends in quadrant number 1. So that's our end behavior. So our end behavior is always going from left to right. And we're saying the left end of the graph is in quadrant number 2. And we're going to use Roman numerals instead of saying just 1. We're going to use 1, 2, This is quadrant number 3, and this is quadrant number 4. So usually you'll see quadrant will be labeled in Roman numerals. So we're going from quadrant number 2 to quadrant number 1. So that's our end behavior. Now we're going to talk about domain. Domain is where the graph exists along the x-axis. So when it comes to exponentials, you're going to find that your domain is all x's. All x's are allowed. If you look at your graph, so I'm going to go back to the picture here, but the graph extends that I could find any value of x. I could continue on and the graph always exists from left to right. So that's what domain is what values are acceptable left and right. So if all values are acceptable, you're going to say x such that x is an element of real numbers. Now we're going to do our range. Our range is where we look at the y coordinates and we say, where's our graph located? Well, I told you that there's not going to be any x-intercepts. The graph is not going to touch your x-axis. The graph is everything above your x-axis. So your graph is located from this point and up. So what that means is that you're going to say y such that y is bigger than 0 YER. Your graph exists where y is above 0. Okay, so that means above the x-axis, above that horizontal line. So that's going to be your range for all of these exponentials if you're doing it properly. And then lastly, we just want to say if it's an increasing or decreasing function. We already talked about that. We said that it's going down, so it's a decreasing function. Okay, so what we're going to do is we're going to graph the next one. 10 in brackets 2 to the power of x. So we're going to start by going to y equals. You're going to clear what's there. And you're going to write 10 in brackets 2 to the power of x. Okay, now our window is still the standard window, so we can keep it as it is for now, and then we'll look at it. But let's see what happens. Let's see if that's enough. So we'll keep it for now at the standard window and just graph it right now. Okay. So let's sketch what we see here. So always make sure that you have these arrows on both ends of your exponential. We label our x and our y-axis. So you want to ask yourself, are there any x-intercepts? And the answer should always be no. There are no x-intercepts on exponential functions, the ones that we're going to look at. So no x-intercepts. Y-intercept, you should say that y is equal to 10 because it's always going to be the same as your coefficient in front of your base. So this is your coefficient. So your coefficient is always equal to your y-intercept value. Then we're going to look at the end behavior. Your end behavior, remember we're saying that this is quadrant number 2. In Roman numerals, we'll have that 2, and this would be quadrant 1. If you notice, guys, you should see that right now what we're looking at is that our graph is going from 2 to 1 as well. So 2 to 1, because it, even though it looks slightly different, it still starts in quadrant 2 and ends in quadrant number 1. Because there's a left end here and the right end's over there. Okay, so it's going to extend eventually to quadrant number 1. The domain should be the same as the previous question. The domain for all exponentials that are not real life questions, that are just equations, numbers, will be XER. And then our range will be y such that y is greater than 0, YER. Okay, so that would be the same for all exponentials if it's just numbers and no situation. Now, is this decreasing? No. If you look at it, it's going up to the right. So it's getting bigger and bigger and bigger. So this is an increasing exponential function. Okay, so make sure you have that filled in there. So we're going to graph our last one, y equals e to the power of x here, and then we'll see what it looks like. Okay, so what you want to do is you want to go to y equals e to the power of x. So I'm going to show you where that e button is. If you guys look, it's right above this ln button. Okay, so there's my ln button, and directly above it in blue, you should see e to the power of x. Okay, so what I want to do is I want to press second button, this blue button here, and then I'm going to press ln. So it's ln, and then you're going to put your power as x. Okay, so e to the power of x. So make sure you can find that. So take a moment and locate that on your calculator. Ask someone around you if you are trying to get this. Now, if you don't have a calculator, a graphing calculator with you, please sit with someone that does so you see what they're pressing and where these buttons are in your calculators, okay? Or in their calculators. So we're pressing e to the power of x. We're going to keep that same window. So once you have e to the power of x in there, now just graph it. Okay, so once you have it graphed, I want you guys to sketch what you guys see in your graphing calculator. So go to your notes and sketch that picture. Make sure you have arrows on both ends of your exponential. Label your x and your y-axis. So what you should find is that there are no x-intercepts. The y-intercept is slightly different. So if you want, you can always press trace 0, enter if you're not sure. But the coefficient, if you don't see any, because this e is actually your base. If there is no coefficient, it's 1. This is what it really is if you don't see a value in front of it. So if you have e to the power of x, your base is e, the value in front of it is 1, even if you don't see it. So your y-intercept is 1 in this case. So remember, you can always press trace on your calculator. You can press 0 and then enter, and it would also say that it's 1. Your end behavior will be the same as all the previous ones. It's going to start in quadrant number 2. The left end is in quadrant number 2, and it's going to go and end up in quadrant number 1. So do you see? 2 to 1, 2 to 1, always left to right. Domain. Your domain is x such that x is an element of real numbers. And your range is y such that y is greater than 0, YER. So it's the same for all of these. So this is a notation that you really want to be familiar with and use all the time. And you want to say y such that y is bigger than 0, YER. We don't put the line underneath that inequality because it's not supposed to touch that x-axis. Okay, so don't touch the x-axis, so we don't have a line underneath to say that it's equal. Lastly, this is an increasing exponential function. So what made something increasing versus decreasing? So I'll show you where I get that information from. So do you guys see how the base is 2 here and the base is e? The base of e just means 2.717 versus over here, the base was 3/4. So if you ever get a decimal value, which if you look at this, 3/4 is 0.75. So if your base is a decimal number less than 1, you're going to find that it's going to be a decreasing exponential. versus if you have a whole number like 2, 3, 4, or 2 point something. So anything greater than 1 will actually give you an increasing function. So I'll get you guys to go back to your definitions page just to write a little quick note here. So in our above equation, when a is greater than 1, for example, like 2 or 2.5 or 2.7, you're going to see that it's going to create an increasing equation. Oh, actually, it should be your b. My bad. So don't write a. It should be b is greater than 1. Okay, so when b is greater than 1, for example, when you have y equals, let's say you have 2 bracket 5 to the power of x. This 5 right here is what I'm looking at. So the base, if it's a number greater than 1, it's going to be an increasing function. Versus if b is a number between 0 and 1, meaning a decimal number or a fraction. So it could be a fraction or a decimal. If your number is between 0 and 1, for example, y equals 2 1/2 to the power of x. So 1/2 is a number of 0.5. That's a number between 0 and 1. So that's going to be a decreasing exponential function. Okay? So that's how you can kind of tell just by looking at the equation if it's increasing or decreasing. Okay, so make sure you have that filled out, those little extra pointers, and then we'll go back to the notes. I'll scroll down. Okay, so what I'll get you guys to do is, Mrs. Swain or the sub, if you guys could pause the video, if anybody's around to pause the video, I want you guys to try example number 4 without your graphing calculator, and I want you to match which equation goes with the missing, with the graph that's given. Okay, so you kind of want to do matching. So does this one go with that one? So match each equation with its corresponding graph and kind of explain where your reasoning is. So I want you to pause the video, and once you unpause it, I'm going to give you the answer and show you how to do it. Okay, so you should have had a moment to try this and to see if you're getting this. So what you want to do is you want to look at each of these. You want to look at the coefficient in front. So here the coefficient is 1. Here the coefficient is 1 over 3. So I'm looking at the coefficients. 1, 1/3, 3, and here it's 1 as well. So I can look at that and tell which of those graphs are going to have the 3 and 1/3, because those numbers that I just highlighted in green, those are your y-intercept values. So your y-intercept values. So I'm going to look for a y-intercept of 3. So if you look, this one has a y-intercept of 3, which means that it has to match up with graph number 3. Okay, so that's the only one that has a y-intercept of 3. So D would be graph or equation number 3. Next, I'm going to look at the 1/3 y-intercept. So 1/3 looks like it's this one right here. So the y-intercept looks like it's about 1/3 here. So that means this has to be graph number 2 or equation number 2. Finally, equation number 1 and 4 both have the same y-intercept, so that doesn't help us. But what does help us here is the base. Remember when I said the base is greater than 1, if the b value is greater than 1, it's going to be an increasing function. Versus here, this one, if it's a fraction or if it's a decimal value between 0 and 1, it's going to be a decreasing function. Okay, so we just have to look at the remaining ones and figure out which one's increasing, which one is decreasing. So this one looks to be the increasing one, so this has to be equation number 1. And this one is the decreasing one, which is equation number 4. And that's our matching. Okay, so what I want you guys to do right now is pause the video and try this group work one to see if you can understand and use logic to answer a real life scenario question. Okay, so take about 10 minutes to pause and try this group work question. Work with someone, work with a few people to see if you can figure this out. When you want unpause, I'll kind of go through the responses. Okay, so group work. 2 students consumed energy drinks that contain caffeine. The mass of caffeine, Y in milligrams, in each student's body was then measured over an 8-hour period. The data is shown in the graph to the left, where X represents time and hour. So these 2 graphs represent 2 different students and their intake of caffeine. So for each graph, we want to determine the y-intercept, domain, and range for these scenarios. So student A versus student B. Student A, the y-intercept is always going to represent when x is equal to 0. Okay, so the y-intercepts are always when time, in this case, is 0. It's always your initial starting point. So where do you start? Well, this graph starts right here and this graph starts right here. So initially, how much caffeine is ingested? Student A ingested 80 milligrams of caffeine because that's where the graph starts at. Versus student B ingested 100 milligrams of caffeine. So those are your y-intercepts. Next, we're talking about the domain. So the domain is going to be different than the previous questions because this is a real life scenario. We can't have our time being negative. So we would say domain would be x such that we'll say that x is greater than 0, XER. And that's going to be the same for the other question right here. Okay, so for the other one, we can see that the smallest time that we have is 0, and it keeps going. Like this graph keeps going here, and this graph continues this way. So we don't know how long it's going to take for that caffeine to completely exit their body. So we're just saying that time is greater than 0. So if we want to be fully accurate, I'm going to do one more adjustment. Time is in hours, H. We're going to use the variable H to represent it. Or, yeah, so we can use the variable actually X. Never mind. They use X and Y, so we're good. Student B will have the exact same thing. X such that time is looked at where time is greater than 0, XER. Okay, so time is not allowed to be negative, which means that we have to look at where time is greater than 0. In this case here, we're allowed to have time being 0 as well. We can look at the time when it's equal to 0 as well. So we're going to say equal to 0. So those are the only differences between the last ones. 2 is before we said XER, but in this case, we're saying that it's going to be 0 and greater. Okay, so that's what that stands for. Next, let's look at the range. So our range, so this was our domain that we just did. Now we'll look at the range. So the range for the first one, we have to look at what the smallest acceptable value is up to the highest acceptable value is. So we're going to say y such that y is between 2 values. We're going to say that the smallest value of y that's acceptable would be where the mass is equal to 0. Okay, so eventually there will be no caffeine in the body. So we're going to say 0 up to the highest value that we see for student A is 80. So we're looking along the y and we're saying what's the minimum to the maximum y that we see. So from 0, we know that the graph goes up to 80. So that's what we just found, from 0 to 80. And then we would say YER afterwards. So this is just a notation that we're using to write it. Now let's look at the range for student B. It's going to be slightly different. The y is going to go in the middle because there's a small value and a high value that we have to cut or look at. So our smallest value is where the mass of the caffeine will be 0 up to the maximum caffeine that we can have in our body, in this case, would go up from 0 to 100. So it's going to go up to 100, comma, YER. Okay, so those are our y-intercepts, domain, and range. Why are both functions decreasing? Well, what's happening is that your body is absorbing and kind of getting rid of this caffeine. So your body is getting rid of that caffeine. Okay, we can't have the caffeine just raising up. It's going to eventually leave our body where we have no caffeine in our system. So this is our body function will do that. Okay, so it's going to start with a high amount and slowly decrease it. Based on the graphs, which student consumed more caffeine? So who initially took in more caffeine? Well, if you look at it, the first student, student A, took in 80 milligrams versus student B took in 100 milligrams. So that means that student B would have more caffeine. Now, which student processes the caffeine more quickly? So who is able to get rid of caffeine better with their bodies? So if you want to look at it, we know that at about 8 hours, it looks like this graph this point right there is a little lower than that point right there. So student B had more caffeine, and yet by hour 8, he has slightly less caffeine in his system. So again, student B is able to process caffeine better than student A. So the answer for both the first question and the second question in C is student B. Estimate the amount of caffeine in each student's body 4 hours after consuming the energy drink. So we're going to look at 4 hours. So you're going to extend your graph and look at this point right here. What is that? So I would say that for student A, it looks to be approximately 20 milligrams. And then you want to do the same thing for student B. So at 4 hours, what's this value looking like? How much milligrams is that? It looks to be slightly less than 20 milligrams. So student B, I would kind of estimate that to say that it's about 18 milligrams. Okay, 18, 17, whatever's close to still that 20 mark. So you're just using the graph to figure out how much mass is there after 4 hours. So you're kind of looking at the side and saying, where does it line up to along the y? So that's what I did for both. Finally, explain the meaning of the y-intercept in this context. The y-intercept represents how much initially they took in as caffeine. So y-intercept represents initial caffeine they ingested. So that could mean how much caffeine is in their drinks. So how much caffeine was in each drink? Why are the values of the y-intercepts different? Well, they're probably drinking different drinks, okay, different energy drinks. Okay, so because they're different drinks, I would assume they're going to have different levels of caffeine in them. Okay, so that's question number E, or question letter E. So make sure you filled out all these notes there. So this is a good application question. It's going to be very similar to the one in your notes. So make sure you kind of take a look at that. Okay, so what we're going to do is this last one, 7.1 takes about 10 minutes. So that's why I included it with this lesson. It's the same stuff, same idea, just a different button that we're pressing to graph a logarithm. Okay. So what I want to show you is the difference between a logarithm and 10 to the power of x. So what I want to do is I want to graph this in my calculator and this in my calculator, okay? So what you need to know about logarithms is that logarithms, the base is always 10, okay? So just like when we have square roots, the index is 2, but we don't write that because it's so commonly used. The same thing with a base of 10. This is equivalent to log base 10 of x. These are the same. If the little number is 10, we don't have to write it, okay? So that's what we're going to do is when I graph it, you'll see that I don't actually include it for my writing. Okay, so what we're going to do is we're going to graph this. Okay, so go to your graphing calculators and I'll show you where this button is. So first we're going to graph the 10 to the power of x because that's the exponential. 10 to the power of x. Okay, so you can see on my screen right here what buttons I'm pressing, and that will help you a little bit. Then you're going to move your arrow down. You're going to use the down arrow, and you're going to go to Y2, and you're going to enter this button right here. So log. You're going to write log of x. Close your brackets. Okay, so log, it's the very left side, fourth button from the bottom. So log of x. We're going to graph them on the same graph just to show you what they look like. So this one, this blue one here is your exponential function. The coefficient is 1 because there is no coefficient. You don't see it. So that's your exponential and your y-intercept is 1. And then in another color, it's going to graph our logarithmic function. Okay, so with your graphing calculator, they don't show them really well. These ones, they might look like they're different, but the blue and the red are actually going to be mirror images of each other. They're going to be reflections, diagonal reflections of each other. So what I want to show you is what they should look like. So when I graph these two functions, we know that one graph is going to look like this. This is your exponential. And what's really important to note is that this logarithm is actually going to look like this. So this is what your calculator shows you. It shows you this. There's an arrow there. What you need to do with all logarithms is extend the line, because what they should do is they should look like the same, but just flips of each other. So if I were to flip it along this line here, this diagonal line, they should look like mirror images. So reflections of each other. So how are they related? They are mirror images of each other. Okay, so let's graph example number 1, A to D, go through them, and we're going to answer those same questions we did for the exponentials, the x-intercept, y-intercept, end behavior, domain, range for each of these following. Okay, so let's go to our graphing calculators, and we're going to do one at a time. Okay, so start by pressing y equals. You have to clear whatever is there on your y1 and your y2. So you're going to start by writing 15 log of x. So you're going to press that LOG button, log, and in brackets, you're going to press x, close that bracket. Okay, we're going to keep the standard window for each of these so you don't have to adjust your window. Once you have this typed in, I want you guys to graph it. Okay, so this one shows a better picture right here of what it looks like. So what I want you to do is sketch that. So if you guys look, you can ask yourself, does it have a y-intercept? If you guys look, it shouldn't touch the y-axis. The y-axis is this right here, so it's not touching that. It looks like it does down here, but it will not. It gets really, really close to it, but it should never actually touch. But in this case, we do have an x-intercept. To find your x-intercept, you're going to press second trace. So second trace number 2. You're going to move your cursor left or right. So do you see how there's a left and right cursor? I'm going to move it until I locate it. There it is. And you want to get as close as possible to your x-axis as you can. So what you're going to do is when you're as close to the x-intercept as you can, you're going to move to the left a few spots. There's the left bound. So as I move left, you're going to see that it's below the x-axis, so this is your left bound. You're going to press enter. Now you're going to move your right cursor above the x-axis, and then you're going to press enter. So what should happen is your left bound and right bound should go on either end of, they should surround your x-intercept, okay? So they should surround your x-intercept. So that's how you know you did it properly, is if those two, in my case, my 2 dotted lines, because I have a version 84, TI-84, if they surround your x-intercept, then you know you did it properly. When it says guess, right here, press enter again. And now it should say your 0. Your 0 is x equals 1. Okay, so we're going to write that our x-intercept is equal to 1. There is no y-intercept. The end behavior is similar kind of to what we did before. We just want to look at first labeling which quadrant is number 1, 2 in Roman numerals, 3, and in 4. Now we have to always go from left to right. So this is our left end. This is our right end. Left end, right end. Because your whatever's left, most left on the screen, what's most right on the screen. So our left end is actually in quadrant number 4, and then it goes into quadrant number 1. So that's our end behavior. It starts in 4, ends in number 1. So that's what you should always find if it's an increasing logarithm. So do you guys see how it's getting bigger? It's getting larger. It's increasing as you go to the right. So this is an increasing logarithmic function. Our domain will be different than our exponentials. It'll be x such that x is greater than 0, xer. And for all of these, it should be, it should look like that. So that's our domain. Our range is y such that y er. It should extend forever. Do you see how there's an arrow downwards and there's an arrow upwards? It should forever extend down and up. So it extends upwards and downwards at the same time, which means that it's going to be every value of y is acceptable. So what you guys should notice is that from an exponential, these answers swap. And so do these answers swap. So in exponentials, your range, this it used to be xer for your domain, but now it's yer. And then for domain, now that it's x is greater than 0, it used to be xer. So those kind of swap locations. And the same thing as your x-intercept and your y-intercepts. Remember how there was no x-intercept previously? Now there is an x-intercept, so they kind of swap their characteristics. So let's go back. So make sure you copy this in. Let's graph negative 5 log of x. So negative 5 log of x. So go to y equals. Clear what's there, right? Negative 5 log in brackets. You want to have x and close your bracket. So remember over here, you can see what buttons I'm pressing. Negative 5 log of x, close my bracket. Let's graph that. Okay, so over here, it looks like the graph stops, but it shouldn't. What you need to always do is extend this line without going across the y-axis. So this is that y-axis, extend it all the way up without crossing it. So what you want to do is draw that now. Show that there's arrows on both sides. Label your x and your y-axis. So you should find that your x-intercept is still going to equal 1. Your y-intercept, there is none, so you'd say no y-intercept. The end behavior goes from, if you guys look, now the left end is up here and your right end is there. So it's actually going to go from quadrant number 1 to quadrant number 4 instead. So left side, the left end is quadrant 1 and the right end is now in quadrant number 4. So it flipped. So you want to say 1 to 4. Domain will be the same, and so will the range be for the previous one. So we're going to say x such that x is greater than 0, xer. And then your range will be y such that y is an element of real numbers. Okay, so this is also when decreasing logarithm, because it's going down to the right. It's getting lower and lower and lower. It's getting smaller as you go to the right, so it's a decreasing log function. Our last two are similar. So we're going to use this ln button, which is a natural logarithm. That's like saying log base e. So what this is equivalent to is saying negative 4 log base e of x. That's what that is the equivalent form of. But there's a shortcut in our calculator. Actually, I'll leave that up so you guys can see. So there's a shortcut for that. We don't want to put that little base of e yet, so we're going to use ln instead. So I'll show you where that is in the calculator. So you're going to go to y equals, clear whatever's there. You're going to write negative 4, and then this is your ln button, your ln button. That's what it's called, ln. So this is when you're doing financial situations, usually they use that base e, so that's why this ln will help you solve for that. So you press ln, and then in brackets, you're going to put that x, close the bracket, graph it. Okay, so once you have this, I want you guys to go and sketch this. And fix that a little bit. There you go. So make sure you label your x and your y, and you have the arrows on either end. So again, the x-intercept should be 1. There are no y-intercepts. The end behavior, whenever it's this one is a decreasing. because it's getting lower. If it's ever decreasing, you should always see that it goes from quadrant number 1 to quadrant number 4. Okay, so it should always go from 1 to 4. So the end behavior should be 1 to 4. So that means it's, if you ever see that happen, that's a decreasing log. The domain and the range will be the same for the next, all of these 4. You just want to practice and make sure you understand why. X is greater than 0, XER. And then your range, Y such that Y, ER. Okay, so that's it for that one. Question number D. So if you guys look, there's a pattern here. Whenever you see a negative in front of a log, so that's -4, that one was -5, you'll see that it's going to create a decreasing function, versus if it's positive like this one and this one, they're going to be increasing. But of course, you can always graph it to confirm that. So I'm going to put 12 ln of x in my calculator. So go to y equals, clear, 12 ln of x. And you're going to graph that. Okay, so take a second and sketch what you see on your graphing calculator. So I have something that looks like this. So you should find that there are the y-intercept and the x-intercept are the same as the other ones. So here you'd say none. There's no y-intercepts. You don't want to put 0 because that would be that would actually be a y-intercept. So you want to say none. X-intercept, you want to say that it's 1. The end behavior, if it's ever an increasing logarithm function, it's always going to go from 4 to 1. So this is quadrant number 4, and this is quadrant number 1. So the end behavior is going to go from 4 to 1 in this case. So it's going to switch compared to the other ones. Domain and range is going to be the same as the previous equations. So you want to say x such that x is greater than 0, XER. And your range is YER for all of these cases. Okay. For your last question, example number 2, all I want you to do is match which equation goes to what. So if you look, 2 of them are exponentials. So these 2 guys are exponentials versus these 2 guys are logarithms. Okay. So for exponentials, we know that here, the value in front, the coefficient is your y-intercept value. And here, the y-intercept is 2. The first one, the y-intercept is 5. So let's look at an exponential function. These 2 guys are exponential. Exponential, exponential. This is a log function, the log function. How I knew that is because of the domain. Here, do you see how it doesn't touch the y-axis? And here it doesn't touch the y-axis, that means it's logarithm. Versus here it doesn't touch the x-axis, and here it tries not to touch the x-axis. Even though it looks like it does not, okay? So that you need to remember that. So for our exponentials, we know that the y-intercept of 5 is going to match graph number 1, okay? So what I want you guys to do is pause the video, try the other ones, make sure that you practice and see if you can do this without a graphing calculator, and then confirm with the answers after you unpause with me. Okay, so you should have filled out the rest of them. But for D, you should find that this one is your decreasing, because this is decreasing, that 0.1. This is a decreasing exponential with a y-intercept of 2. This one, the y-intercept was 5. That's how I knew it was graph number 1. And then we have here, this one's a decreasing, which means that the log should be negative. So do you see that negative in front? That means it's decreasing. So then that one has to be graph number 4. And finally, this one has to be graph number 3 because it's an increasing exponential, or sorry, increasing logarithmic function, okay? This is just a summary sheet of what you should find. So what we just did in this lesson is summarized here. So this is just a summary of what we just covered if you want to take a glance of that. And then I want you guys to go back to your definitions page just to fill out the last definition for today, and then we're done. So a logarithmic function is just a function where you have y equals log of a base b of x. So this is now your base value, okay? So what it's going to look like when you graph it, it's either going to be this if it's increasing with 2 arrows on either side, or it's going to look like this if it's a decreasing logarithm, okay? So what these are helpful for these are used in a lot of applications. So we use this in earthquake magnitude and all this stuff. So we'll get into that later on. But right now we're just kind of focusing on the exponential. So we will get into the logarithms later on. So make sure that you have all these definitions filled in. And then if there's time at the end of the class, I do want you guys to practice. So use your notes and use your textbook to answer and finish day 1 homework.